use the alternative definition of curvature to find the curvature for the following parameterized curve. So here we are given the vector-valued function, vector r of t, defined by the components 6 plus t squared, 2t, 0. And again, we are being asked here to specifically use the alternative definition. So we need to take our position vector, vector r of t, and find the velocity vector and the acceleration vector. So we, of course, know that the velocity vector is equal to the tangent vector. So differentiating our position vector, we have 2t, 2, 0. And notice we have a scalar multiple of 2. So I'm going to pull that scalar multiple 2 to the front. So we're left with the velocity vector 2 times vector t, 1, 0. So since we have this velocity vector, might as well take it one step further to get the acceleration vector, which we know is the derivative of your velocity, or the second derivative of the position vector. So differentiating the velocity vector, we're left with 1, 0, 0. So here we go. We've got our beautiful velocity vector, as well as this acceleration vector. And now looking up at our alternative definition, let's go ahead and take the cross product of these, since we need the magnitude of that cross product. So we are crossing the velocity vector with the acceleration vector. So this is the cross product of 2 times the vector t, 1, 0, crossed with the vector 2 times 1, 0, 0. So just keep in mind here with these scalar multiples, we can keep those in front of that 3 by 3 determinant. So 2 times 2 leaves us with 4. And now for the cross product of the two vectors, I'm going to put that right into the determinant of the 3 by 3 matrix. So the first row is I hat, j hat, k hat. The second row is t, 1, 0. And our third row is 1, 0, 0. So again, just be mindful keeping that scalar multiple of 4 on the outside of the cross product. We are left with, so by definition, we have 0 minus 0 I hat minus 0 minus 0 j hat plus 0 minus 1 k hat. So the cross product is defined by the vector 4, 0, 0, minus 1. So there we have it. There is the cross product of the velocity vector with the acceleration vector. And now we're ready to go ahead and use this to find its magnitude. So the magnitude of the velocity vector crossed with the acceleration vector, and again, I'm going to keep my 4, my scalar multiple, on the outside of this distance formula. So we have 0 squared is 0, plus 0 squared is 0, plus negative 1 squared is 1. So we have 4 multiplied by the square root of 1, which is just 4. Woohoo! So this is the first part that we need, the first component, if you will, the numerator of our alternative definition. And so now we're ready to find the denominator. So we need to find the magnitude of our velocity vector. So keep in mind here, we found in the very first step, we found the velocity vector to be 2 times the vector t, 1, 0. So finding the magnitude of this, we'll keep our scalar multiple 2 out in the front. So that's going to be 2 multiplied by the distance formula. So we have t squared plus 1 squared plus 0 squared, and we can just leave that 0 out. So there's the magnitude of our velocity vector. But don't forget, we need to cube this. So let's give ourselves a little bit more room. All right, so taking our velocity vector that we just found and cubing this, we have 2 times the square root of t squared plus 1 cubed. So we can think about this as 2 cubed multiplied by, and I'm going to rewrite that radical in its exponential form. That's t squared plus 1 to the 1/2 cubed which leaves us with 8 multiplied by t squared plus 1 raised to the 3/2. So this is the magnitude of our velocity vector cubed, and we have everything we need now to find the curvature. So our curvature kappa, using the alternative definition, is defined as the magnitude of the velocity vector crossed with the acceleration vector, all divided by the magnitude of the velocity vector cubed. And plugging everything in, we have 4 in the numerator, all divided by 8 times t squared plus 1 raised to the 3/2, which of course we want to simplify. We know 4 goes into 8, 2 times, for a beautiful final answer. Our curvature kappa is defined as 1 divided by 2 times t squared plus 1 raised to the 3/2. And so this is our final answer for curvature using our alternative definition. And keep in mind that while we used the alternative definition here, we will get the same answer if we use the computation definition we derived from the intuitive definition.